Welcome to this technical HOT session, HOT Heidelberg OSADL talks on Linux tracing and debugging, particularly troubleshooting and particularly what we call latency fighting. Latency fighting, you may have heard about our latencyfighting@osadl.org email address. You may have heard about histograms where the time information is lost. And you may have heard of our well-known culprit victim tables, where we reinstalled the lost time information in addition with the information about kernel threads that were involved in a latency, so the one that was hindering the next task to run, the culprit, and the task that was hindered, the victim. And we use this in order to find the underlying mechanisms, the underlying sources of a latency, in order to fix it. Again, the histogram shows an outlier, but you only know that during the entire measurement of this histogram, the outlier occurred. You don't know when, and you don't know under what condition, and you particularly do not know what was the part of the system that is responsible for preventing the real-time process of being switched to in time. And we now will have a look at such examples. We call this latency fighting. So here's a standard latency plot. Again, linear x scale, logarithmic y scale. The system is answering nearly all the time in a very fast manner. Then some outliers here. They may not be that important, although the curve looks so nice and it looks very obvious that the curve itself is one component of the system and then these peaks are another component. And first of all, we would like to remove those. But then it is also very important not only to look at the curve, but only to look at the legend, which tells us that there's some outlier completely out of the scale at 16.9 milliseconds. And if you look very closely to the x scale, you see that here's another nearly 200. So we probably have two, this and this very far away, 16 milliseconds, and maybe a third mechanism causing latency. And we cannot argue that most of the time the system is fast. No. The system loses its real-time capability at the moment when a single outlier occurs. And we need to, understand why this happens. And if we cannot remove this after a single measurement of this kind, an unresolved resource, the system can no longer be used as a real-time system. Fortunately, we have our culprit victim table, where we look for those cases. Well, I should have said this, of course, this was done with cyclic test. So cyclic test was the one that was prevented from being in time. And so we look for the culprit cyclic test. And what we see here is mod probe. So 2 times at 16 milliseconds. And then there's another one at 196. And so it looks like we have found exactly these 3 latency values. So let's again compare. There's one at around 200, and there's at least one at 69. And then we look at the culprit table, and here they are. Exactly the same values. And for the first time, we know when, on what core, and by what program this happens. Okay, but mod probe? Why mod probe? Why could mod probe ever create a latency? Well, mod probe is never intended to be used to run while a system is running under real-time conditions. It doesn't make sense. Mod probe may involve initialization of a chip, may involve functionality that was never intended to be run under real-time conditions. So that's okay. The fact that modprobe is creating a latency is one thing, but the other fact is that modprobe is running while cyclic test is running. This is another story. So we need to find out what happens here. By the way, we still have the Moonin plot, the Moonin functionality running, which takes every 5 minutes values, and this helps also to re-establish the relationship between the timing and the latency. So you see here this 16 millisecond outlier at exactly the same time. So this helps a lot, and you see here the 2 cores that have been affected, exactly the same course as the one that we have seen in the culprit victim table. So let's go ahead and have a look at the D-message output. We see 2 things. One is that obviously the cooling didn't work well with this processor, or the requirement, the performance requirement was too high for the cooling, one or the other, and the automatic thermal throttling occurred, which means that the clock frequency is slowed down in order to allow the cooling system to recover. We know that this affects latency more or less in a proportional way. So let's say that this is a 2 gigahertz processor, and that, for example, throttling caused the processor to throttle down to 1 gigahertz. This would result in a latency from, for example, 50 microseconds to 100. Again, frequency, clock frequency and duration of a latency is more or less proportional. So this would not explain what happened here. But then at the end, we see a hardware error, machine check exception, and machine check event was logged. And this is a combination of a kernel part and of a user space part. And the disassembly of this message is normally taken by a user space program, and this user space program needs a driver to talk to the machine check variables. And this is the MSR module that normally is not available, was not available, and as you can see here, because it is on the first position, it was most recently loaded. So we can now reconstruct this latency. By some reason, the system became too hot. Maybe performance requirement too high, maybe cooling not good enough. In response, the kernel throttled the frequency, which is, well, good to know. Certainly we would have seen this, but this normally would not create such a big problem. But then by some reason, the cooling was not strong enough to recover. The throttling was not effective enough. And then the system generated a machine check. And to decode this machine check, a driver was loaded. And this driver then caused a very long latency during initialization. Is this a bug? Well, yes or no. It is a bug because all driver programmers should try their very best not to disable interrupts too long. But maybe this machine check mechanism requires it. We don't know. Maybe the only way to initialize it is to stop interrupts for 16 milliseconds, which may be also a shortcoming of the hardware design. But okay, it happened, and we need to find a solution to this. Better cooling, but even with the better cooling, it would be good to make sure that this does not happen. So what we could do is that we load the MSR module immediately after the system was booted. And then this long latency would not occur during run of the real-time system because it is done initially when real-time is not yet important. Well, it's a quick fix. It may or may not fix the situation. Then we may file a bug, of course. But at this time, when Linux is not yet fully equipped with real-time, we always need a patch. it's not that easy to ask the MSR module programmer to make sure that the system works also under real-time conditions, because when the kernel is initially released, it has no real time. So the person may then tell you, well, I don't know, this is an off-trip patch. Look, this is another important reason why we really are looking forward to getting all these patches into real time, into the mainline kernel, so that next time when such a problem occurs, we can write to the programmer, to the Linux kernel developer without any problem and ask them, please fix it, because real time is part of the kernel. Well, the person may then not want to do it or whatever, then we can fix it ourselves. Look at the initialization part of the MSR driver. Why is there a need to stop the interrupt so long? We can search for busy loops while preemption or interrupts are disabled, and provide little windows so that the system may need the entire time, but not under the condition of disabled interrupts. There's the break trace feature of the cyclic test tool, which we can try to find very clearly what happens and to fix it. We may also try to shorten the loop, because maybe the programmer, as I said, was not aware of this real-time interference. So there's a lot of things to do. Maybe even the quick fix works. But the example, we showed here to you the example, of course, to exemplify the use of culprit victim tables. Let's have a look at case number 2. Case number 2 is again the shape of the curve. What we see here is a very close to zero peak and a very steep curve, the shape of which would probably go to something around 10 microseconds. This is a fantastic value. The system could then maybe even use for motor control or tight loop controlling. So this would be good. But then we see a little curve, a plateau here in the range of something around maybe 800 samples, 700 samples in the amount of 40 microseconds. So something in the system is causing repeated 40 microsecond, up to 40 microsecond latency values. Well, it may not be a problem, because your industrial control system requires something around 500 microsecond, and on this 38 still is good. But well, from the engineer's standpoint, we see this curve, and the shape of this curve is strange. We really would like to improve this curve and to remove this, and would want to understand what it is. And maybe we are board manufacturers or, well, kernel developers or whatever, and we would like to create a universally useful kernel for every purpose, including very low latency requirements. And then, of course, it is a very good idea to get rid of this plateau here, which doesn't look to belong here. Of course, what we do next is we look at our culprit victim table. And what you see here is, again, cyclic test is the victim. And we see pretty much these values close to 40 microseconds here. So this corresponds very well to what we have seen in the latency plot. And then, surprisingly, what we see here, our culprit is an interrupt. Interrupt number 16, connected to the Ethernet controller and the device with the name ENP2SOFO. What is this? Let's have a look at it. It is a Broadcom Netlink Gigabit Ethernet PCI Express network device. And, well, it is very probable that the interrupt execution of this device in close collaboration with the device is responsible for the problem. So let's unload it. And just for testing, let's replace it by a USB network controller. So we use one so that the interrupt number 16 is no longer used for this. and then replace it, and everything works well. Hopefully. We will see. We will test, of course. So what could you do? Same procedure as before. Let's file a bug and answer the programmer to check what's going on. And then again, they may argue or not argue in favor or not in favor of real-time. Another reason why, of course, we are looking forward to getting real-time to mainline. But if nobody helps us, we even may do it ourselves. And the procedure, again, is the same. When we fix it, we analyze the source code and we check whether there are busy loops that disable interrupts for longer than necessary. Or we can use the cyclic test command to get more information about the single instruction being involved. And maybe we find a busy loop that we can shorten, or we can remove, or we can replace by something else. It depends on the driver. So let's have a look whether this is true, whether our suspicion was correct. This is the same plot as the one you saw before with the curve. And then we replace the controller. We replace this PCI Express built-in controller by a USB controller. And once we do this, it's gone. So you can very easily use this method and to check whether the removal of the suspicious driver helped. Latency fighting case number 3. What was here the case? An 8-core system. This looks again good. Could be a fast, responsive system, but it is not. It goes up to 70 microseconds, even a little bit more than our rule of thumb would be required for this more than 2 gigahertz system. So we would have expected 40 microseconds as the maximum, but it goes up to 70. And again, it looks like 2 completely different mechanisms. One, the normal curve, the normal latency plot curve, and additional latency values randomly interspread here into this plot. And we would like to understand what it is. Again, of course, culprit-victim table. Cyclic test is a victim. The latency values correspond very well to those we have seen. Cyclic test is the victim, and meminfo is a culprit. So what is this? Meminfo. Meminfo is a Munin plugin that gives very detailed information about the various memory subsystems, inclusive the various cache handling mechanisms. So it already helped a lot in diagnosing memory problems of systems, and it is something that is enabled by default. But the way of how meminfo is able to produce information depends, of course, on the way the kernel is providing the information. And most systems normally do not have debugging of slap info enabled, and this is why the certain limited information is produced by proc slap info. By the way, when we switch to real time, the slap allocator is replaced by the slap allocator. So this is a little inconsistency that slap info provides slop information, and but it still can be inspected through the same interface. And normally it is not a problem because when debugging is not enabled, the information is not taken from so far, and in consequence there's no interference with real time. But sometimes, and this happens because one of the distributions we used had the slap debug configuration enabled by default, and this is why we run into this problem. This is just an overview about what slap info can do for you. It can provide well information. We're even every single part of the kernel memory allocation is then displayed and plotted. And as I said, it already helped us many times to diagnose memory problems. So yes, this is why meminfo is innocently configured in our system. And again, we never had a problem. But then we found that this particular system has config slab debug enabled. And because of this enabling, the proc slab info went much more deeply into the kernel to collect information than it was normally the case. So the quick fix, well, it may not be a fix if you rely on this information, but the quick fix was to just remove this slab debug equals yes, and put the config slab debug is not set in and rerun the system, and then hopefully this latency would have gone. But then, of course, we would like to really understand what's going on, and then we created a patch. And this patch was based on the fact that initially, at the very beginning, when the system started to look for the memory, the various bits and pieces of the memory, it started a lock which blocked the system and created the latency, and then it ran through the entire tree of memory information, and only when it came back at the end, then the lock was removed. This created long latencies. And what we then did, we removed this one, and then we added it at a lower level, so at the level where the individual parts of the cache were inspected. Disadvantage, the entire information may no longer be coherent. So it may not add up to the total information, but it may then be able to remove the latency. So the reason for it was to create consistent information of the entire cache information. So it was not a bug, it was something they did with good reason. But in the light of real-time execution, this is not a good idea. And one could imagine to investigate the system further to, at the same time, provide consistency and no real-time effect. But, well, you cannot have everything, and so debugging always involves a certain, we call this sometimes Heisenberg effect. So whenever you look at it, you may modify it, and this is here the case. It was modified. But still, in order to prove whether what we did is correct, we do this before measurement. This is exactly the same plot as the one you have seen before. And after we removed, either we removed the debug feature or we implemented this patch by lowering the lock level from the total lock to one level below, then the problem is gone. And we have the nice curve that we expected from the very beginning. Again, we were able to locate the underlying mechanism and to understand why the system had this latency. We removed it, we found several ways to remove it, and then the system went back to the expected real-time behavior. We hope that we were able to give some examples of how the built-in histograms, again, something that was in the kernel patch before, but now is maintained by OSADL, which you can download per kernel version and patch your kernel so that you get these culprit tables and be able to fix your system and to remove any unwanted latency. Thank you.